Buenas tardes a todos, bienvenidos a esta conferencia. Y es un gran placer para mí presentarles a Wendy Freedman. Su formación como científica procede de Toronto, de Canadá, donde realizó sus estudios y obtuvo su doctorado. Y creo que desde hace relativamente poco es profesora en el Departamento de Astronomía y Astrofísica de la Universidad de Chicago. Y digo esto porque entre estos dos acontecimientos, la carrera profesional de Wendy Freedman ha estado ligada durante unos 30 años a los observatorios Carnegie en Pasadena, California, donde comenzó como investigadora postdoctoral en 1984, llegando a alcanzar el puesto de directora, algo no tan común para una mujer. Y esto fue en el año 2003. Esta institución es la base del famoso telescopio de 2,5 metros de Mount Wilson, y con él Edwin Hubble obtuvo las observaciones de un buen número de galaxias, descubriendo que se estaban alejando de nosotros y dando lugar a lo que conocemos como la ley de Hubble de recesión de las galaxias. Con este telescopio también se observaron las primeras estrellas variables cefeidas en galaxias distintas de las nuestras. Y la carrera de Wendy Freedman está muy ligada a estos dos estudios pioneros. La ley de Hubble, obtenida empíricamente, nos dice que cuanto más lejos se encuentra una galaxia, más rápidamente se aleja de nosotros, y estas dos cantidades, distancia y velocidad de recesión de las galaxias, están relacionadas, como no, mediante la constante de Hubble, que de acuerdo a los modelos cosmológicos actuales, pues mide la velocidad a la cual el universo se expande. Y en principio nos permite conocer el tamaño del universo visible y también su edad. Bueno, al comienzo de los años 80 del siglo pasado, el valor de esta constante se conocía con una presión de solamente un factor de 2. Y Wendy Freedman dedicó una buena parte de su carrera a dirigir un equipo de 30 científicos que diseñaron y realizaron las observaciones con el telescopio espacial Hubble para medir la velocidad a la cual el universo se está expandiendo. ¿Y cómo se realizó este trabajo? Pues a través de la observación de estrellas cefeidas en distintas galaxias. Y gracias a esta colosal investigación sabemos hoy que la edad del universo, que antes se estimaba entre 10 y 20.000 millones de años, en realidad es de 13.700 millones de años, con una incertidumbre de solo un 10%. Y este fantástico resultado fue fruto de muchos años de trabajo y le valió a la profesora Freedman, junto con su equipo, la concesión del prestigioso Premio Profª de Cosmología en el año 2009. En la actualidad, el trabajo de Wendy Freedman se centra ahora en medir la velocidad de expansión del universo, también en el pasado, y caracterizar así las propiedades de los que ha venido a llamarse energía oscura. La profesora Freedman también está muy involucrada en el desarrollo y construcción del telescópico Magellan gigante en el Observatorio de las Campanas, en Chile. Estos son 7 espejos de 8,4 metros que combinados van a funcionar como un telescopio de casi 25 metros y que esperamos esté en funcionamiento durante la próxima década. Y con él imagino y espero que Wendy Freedman seguirá encontrando sorpresas en el universo, porque ese es precisamente el título de su conferencia, El universo, una constante sorpresa. Y espero que la disfruten.
Muchas gracias por la introducción. Es un placer estar aquí en Madrid, una ciudad muy hermosa, y muchas gracias por la invitación. Me gustaría poder continuar en español, pero yo no tengo el vocabulario astronómico. Por lo tanto, yo voy a cambiar al inglés. And I hope I'm not disappointing anyone if you thought I was going to continue in Spanish. My topic this evening is the unexpected universe. And as I will tell you more tonight, we have continued to learn things in the last century that were completely unanticipated. We thought at the beginning of the last century that the Milky Way galaxy, our Milky Way galaxy, comprised the entire extent of the universe. We thought the universe was much smaller. And in the last century, we have learned that the universe is filled with galaxies like our own Milky Way. Moreover, that the universe itself is expanding, and we are not made of what most of the rest of the universe is made of. Most of the mass in the universe is in a form that we cannot see. We call it dark matter. And the universe is filled with a kind of energy, which astronomers now call dark energy. And about 2/3 of the overall universe is made up of the dark energy. And 95% of the universe is in a form that we knew nothing about only a few decades ago. We've learned also that there are planets outside of our own solar system. Before 1995, we knew only of the planets in our own solar system. And there are thousands more candidates, and each day, in fact, new discoveries are being made. Very soon, as I'll describe, we are going to have telescopes that will be capable of finding planets that are like the Earth in their mass and their density, and perhaps even conducive to supporting life. So one of the surprises for me this afternoon was being able to go to the Prado, which was an unexpected treat for me. For those of you who know the Prado, of course, that's nothing new, but it was a really delightful afternoon for me, and I thank you again for that opportunity. I'm going to take you now to the Andes Mountains in Chile. This is Las Campanas. It's in the Atacama Desert. And at the moment, we have telescopes at a scale size of 6.5 meters. There are 2 telescopes at Las Campanas Observatory. And it's the site of where the giant Magellan Telescope will go, and I will speak more of that toward the end of the talk. But now, in various parts of the world, of course here in Madrid also, the city lights really do prevent us from looking up at the night sky. And most children growing up today may never have seen a dark sky if they're growing up in a city. And so astronomers, as you know, go to very remote parts of the world, the Atacama Desert being one of those places. And this is the Magellan Telescope looking up at the Milky Way, which is located, of course, in the southern hemisphere. And the southern skies, in the next couple of decades, there's a lot of activity in the southern hemisphere right now. New telescopes that are being planned and new telescopes that are being built to study the sky at optical wavelengths and also radio wavelengths. And then, of course, there are new facilities that will be launched into space in the next decade, including the James Webb Space Telescope, which is the successor to the Hubble Space Telescope, that will be launched in 2018, and then a number of other satellites, including the Euclid satellite, which will be launched, European satellite, something called WFIRST, which is a NASA mission, and telescopes that are very sensitive to radio wavelengths. One has just been commissioned in the southern hemisphere called ALMA. So together, this suite of new telescopes, including 3 giant telescopes, one of which is the giant Magellan Telescope, are going to open up, I think, a very new window of opportunity and discovery for astronomy. There have been 3 major discoveries in cosmology over the last century, starting with Edwin Hubble and the discovery of the expansion of the universe in 1929, and then the discovery of the evidence for dark matter, although we have not yet discovered what we believe are the particles that comprise the dark matter. And then right at the end of the last century was the discovery that the universe is not only expanding, but it's speeding up in its expansion over time. It's actually accelerating. So I'm going to walk through those discoveries, starting with Hubble the man, Edwin Hubble, and Hubble, the Space Telescope, after whom Edwin Hubble, after whom it's named. And Edwin Hubble came to Mount Wilson in Pasadena, California. He was at what are now known as the Carnegie Observatories, where I spent 30 years of my career until this past September when I moved to the University of Chicago. And Hubble came to Pasadena as the telescopes at Mount Wilson were being constructed. The director at the time was a man by the name of George Ellery Hale, and Hale built at his time 4 of the largest telescopes successively in the world. Quite an extraordinary feat. He started with a refracting telescope made of lenses at Yerkes Observatory, a 1-meter telescope, moved out to Pasadena, convinced the steel magnate, Andrew Carnegie, that progress would be made in astronomy if large mirrors made out of reflecting glass could be made. And Hale was responsible for building a 60-inch, 1.5-meter telescope at Mount Wilson, then a 2.5-meter telescope at Mount Wilson, and eventually the 5-meter telescope at Palomar. And Edwin Hubble came as a young man in the 1920s, and he was interested in studying objects that were referred to as nebulae. A nebula is a Latin word, and it means fuzzy. And here's an example of a nebula. This is the Andromeda Nebula, and in fact, it's actually visible to the naked eye in the northern hemisphere on a very dark night, very faint and fuzzy because it's far away. But in a telescope, it reveals itself to look like this, fuzzy if you don't know what it is. And Edwin Hubble began to observe with the telescopes at Mount Wilson, first the 1.5 meter and then eventually the 2.5 meter. And he took a series of photographic plates of galaxies like Andromeda. And what he found was that there were small pinpoints of light. You can perhaps see some of these here, tiny little dots, and in the rim of the galaxy also, of the nebula. And what he noticed was, when he came back over time, the brightness of some of these images, and it turns out about 1 in 1,000 of the ones that we see, changed in brightness over time. So if we look up at the night sky and we see stars in the sky, most of those stars never change in a human lifetime. We come back night after night and it's really kind of boring because they don't change. There's nothing new on a human lifetime, human timescale. But what Hubble noticed was that some of these points of light were varying on timescales of days, maybe months. And the stars would get brighter and then they would get dimmer. And they would do that over a period of time in a very characteristic way. And Hubble was able to show that this class of stars, which resembled a class of stars that had been discovered in the 1700s, called Cepheid variables. And these are stars that allow astronomers to measure how far away an object is. And I'll describe more of that in a minute. But with the discovery of Cepheid variables in the Andromeda Nebula, Edwin Hubble was able to show that this is an object like the Milky Way. Our Milky Way galaxy contains probably something like 100 billion stars in this galaxy alone. And that there are many other galaxies outside of the confines of the Milky Way galaxy. So it's an extraordinary discovery. Suddenly, essentially overnight, what Hubble was able to show was that we are not the only galaxy making up the universe, but in fact, as we know now today, there are about 100 billion galaxies in the part of the universe that is accessible to us, where we can see. So these objects have about 100 billion stars within them, and there are about 100 billion galaxies that we can see. So that was a revolutionary discovery. If it was the only discovery that Edwin Hubble had ever made, it surely would have assured him place in history. But he went on to discover, first, not only were there other galaxies, so galaxies with different shapes and sizes, beautiful objects with these spiral arms. In fact, our Milky Way galaxy also has these arms that have this nice, beautiful spiral pattern. If we were able to look at our Milky Way galaxy, get outside of it and look back at it, we would also see the spiral arms of our own Milky Way galaxy. Others we look at from the side. Here are more galaxies. And we also see galaxies that are colliding with each other. They actually are colliding. Some of them merge together, and they change over time. And this is another galaxy that recently underwent a collision and a merger. So Hubble was able to discover that we are not the only galaxy in the universe. So telescopes, I want to emphasize, have really changed our view of the universe. And of course, this is the familiar Hubble Space Telescope, which orbits about the Earth every 90 minutes. So it is above the atmosphere of the Earth. And that, for astronomers, allowed us for the first time to get a glimpse of the universe at optical and ultraviolet wavelengths, free from the effects of the turbulence, the motion in the Earth's atmosphere. So Hubble allowed us to increase the clarity or the resolution, the fine detail that we can see by about 10 times from what we could do routinely with telescopes on the Earth. And so astronomers anticipated with great interest the launch of the Hubble Space Telescope in 1990. Really allowed for enormous new discoveries. So here is the Hubble Space Telescope. We're looking now at a video of the telescope looking down on Earth, and the telescope allows us now has allowed us to make measurements of Cepheid variables in galaxies. It's allowed us to make measurements of very bright explosions called supernovae. The numbers of discoveries that have been made with this telescope really are enormous. People have studied planets with the telescope and to study the nature of dark matter in the universe. Here are more examples of galaxies that were imaged with the Hubble Space Telescope. So here's another pair of them. Those galaxies will merge by their mutual gravitation, the gravitational force between them in some billions of years in the future. And you can see these really astounding, beautiful images. I think there's no other way really to describe them. These long tails that are caused by the interaction due to gravity tidal forces that pull out material as galaxies merge. So here's an example of a galaxy that we studied with the Hubble Space Telescope. It's a galaxy known as Messier 100. So this actually is an object that was discovered by a French astronomer working in the 1700s by the name of Messier. Messier noted all of the objects that he thought were boring, that he could throw out. And the reason was he was interested in studying comets. And so whenever he found something that was fuzzy, that wasn't a comet, it went on his list to discard. And unfortunately for Messier, what he's best known for today are the objects that he threw out, the Messier objects. And what I'm showing here, you can see in these blinking points of light here, are stars that are meant to represent Cepheids, these variables that are changing in their brightness that allow us to measure distances. And this is not a real picture of Cepheids. They actually vary on timescales of a few days, as I said, up to a couple of months. But what I'm trying to illustrate here is that the brighter stars vary more slowly than the fainter stars. You can see that the fainter stars blink very fast. And that property was discovered by an astronomer by the name of Henrietta Leavitt, who was working at the Harvard College Observatory in 1908. And she discovered that there's a relationship between how bright a star is. So the brightest stars change in brightness very slowly, whereas the smaller stars very, very rapidly. So there's a unique relationship between how bright a Cepheid variable is and how fast it's varying. And that property can be used if we can find Cepheids in galaxies other than our Milky Way, where we can determine the distances very accurately. Then we can compare the brightnesses at the same period and use something called the inverse square law, which allows us to determine the distance, because the brightness falls off as the distance squared in the same way that the force of gravity falls off with the distance squared. And that unique relationship is what Edwin Hubble used when he first discovered the Cepheids in Andromeda, and what we use today when we use the Hubble Space Telescope to measure Cepheids in these galaxies. And it remains the most accurate means that astronomers have for measuring the distances to nearby galaxies. And that's what we used with the Hubble Space Telescope. And more recently, we've used a sister satellite to Hubble. It's called the Spitzer Space Telescope, and it is sensitive to very red, very long wavelengths. And that has a number of advantages. So in addition to the work that we did with the so-called Hubble Key Project in the 1990s, we've been extending our work more recently to use this other satellite that allows us to make very accurate measurements and refinements to our original work. So the idea is we create a ladder. We step out in distance. We can measure stars that are in our own galaxy. Then we can measure stars that are in galaxies like Andromeda. Then we can measure bright supernovae, these explosions of stars that happened at the end of the lifetime of a star that can be seen to great distances, much greater than the Cepheids because they're so much brighter. And that way we can step out into the universe and measure the expansion rate now and also the expansion rate in the past to see how it's changed. So this was a Time magazine article in 1995. This is the same galaxy, Messier 100. This was when we got the first observations from the Hubble Space Telescope. And what turned out at the time was that there was a controversy between the age that we were estimating based on measuring how fast the universe is expanding now compared to the age of the oldest stars in the universe, in our own galaxy, where we could measure them directly. And so that was something that we didn't understand at the time until the acceleration of the universe was discovered later in the decade. And that helped to resolve this issue of the age. We now know that the age is something like 13.7 billion years old. And this is the original data. So what I'm showing here, and this will be the only plot that I will show in the talk, but just to give you a sense of what Hubble did in 1929 is he plotted the velocity of the galaxies that he was looking at, things like the Andromeda galaxy, compared to the distance of the galaxy that he was measuring, mainly with Cepheids. And he noticed that the farther away a galaxy is, so galaxies that are to the right at greater distances, have higher velocities. They're moving away from us faster than the galaxies that are nearby on the left of this plot, small distances, small velocities. And so the slope of that relationship is something that we call the Hubble Constant. Hubble measured a value of over 500 for this measurement. And what we did with the Hubble Space Telescope, you can see actually Hubble's original data fit into this first tick mark here on the plot. So today we can measure distances much farther out than Hubble could in his day. And so he measured a value of about 500, we measured a value of about 70. And that leads to a determination of the age of the universe of 13.7 billion years. And before the Hubble Space Telescope, we didn't know the age to better than a factor of 2. Astronomers were undecided as to whether the age was 10 billion years or 20 billion years. And with the data that we could get from telescopes on Earth, it wasn't possible to make the measurements with as great precision or accuracy as we were eventually able to do with the Hubble Space Telescope. So in terms of the evolution of the universe and what we have learned in the last century is that if you take the result that the universe is expanding, what Edwin Hubble discovered, and you run it back essentially like a movie in reverse, and you use Einstein's general theory of relativity, which is a theory of gravity, which allows you essentially mathematically to run the universe, evolution of the universe backward in time, then what you find is today you see galaxies in every direction that we look. If in the past if the universe has been speeding up over time, then they were closer, those galaxies in the past. You keep going back further and further in time, then there would have been a time when the galaxies literally would have been on top of each other, where there would have been a very dense period of early in the universe where matter was very densely collected into a very small region or smaller region. And it would have had a very high temperature. So there would have been a period in the universe, very high density, very high temperature, something that we refer to as the Big Bang. In the last couple of decades, it's become clear that there also was likely a period when the universe was very, very young with a very rapid period of acceleration. That's called an inflationary period. And literally it took place in a fraction, very tiny fraction of a second in the earliest moments of the universe. And we see today the universe in the microwave background radiation. So this is the cooled radiation from the Big Bang. About 380,000 years after the Big Bang, we see small differences in temperature when we look at the radiation that permeates all of space that is from the Big Bang explosion. And today we see galaxies, as I've shown you, about 13.7 or 13 billion years after the Big Bang. So that's the overall evolution of the universe. And there's a period, which I'll just point out now, after this region where we can measure the cosmic background radiation and where we measure the first galaxies, where we know nothing about what happened. We haven't had the technical ability to look at that time in the universe. We see galaxies today, we know they're here, we live in one, we see the remnant radiation from the Big Bang, but there's this period where we know nothing. And that's one of the areas that we hope to study with the new generation of large telescopes like the European Extremely Large Telescope and our own giant Magellan Telescope. So I mentioned most of the universe is made up of a form of matter that is dark. And you may ask, well, how do we know it's there if we can't see it? And it's an interesting story. In fact, in the 1930s, the first evidence for this matter that we can't see was detected. It was found by an astronomer at the California Institute of Technology by the name of Fritz Zwicky. And what he noticed, he was studying a group of galaxies, a cluster of galaxies. Galaxies tend to be located near other galaxies because of their mutual gravitational attraction. They probably form close to each other in dense regions early in the universe. And he measured how fast the galaxies were moving in the cluster. And what he found was the galaxies were moving so fast that they should have flown away from each other long ago because there wasn't enough mass there with the force of gravity to keep the clusters bound, attached to the cluster itself. They should have flown off long ago. And this was in the 1930s. Astronomers essentially ignored the result because it was too strange. What did that mean? There was matter there that we couldn't see, and people thought, well, maybe there's something wrong in the observations or the idea, or nobody really thought very hard about it. But for about 40 years, the evidence continued to accumulate. Still, people didn't pay attention to it until the 1970s, when people also found evidence that not only in clusters of galaxies were galaxies moving very fast, but within galaxies, the stars were also moving much faster than they should if there wasn't more matter there to hold on to them. And in the 1980s, it became possible satellites were launched that were sensitive to X-rays, very hot gas in clusters of galaxies. And you can see here a map of the gas that's measured in a cluster of galaxies, very hot. Should have evaporated long ago, again, if there wasn't more mass there that was holding the gas to the cluster. And one of the predictions of Einstein's general theory of relativity is that as light is coming through a massive, say, cluster in a universe, then the light that's coming from galaxies behind the cluster will be lensed, as if you had an actual lens, and distorted. You can see these features here, the sort of long features, filaments that are strung out because of the effect of the mass in the cluster that's distorting the light from galaxies coming behind. So that was predicted by Einstein's theory. It wasn't discovered until 1979, and now we see, this is an example from the Hubble Space Telescope, we see literally hundreds of examples of this. So all of these very, very different experiments are pointing to the same result. There is matter in the universe that we don't see. So we see galaxies, this is a nearby cluster of galaxies, we see the galaxies, but there's more matter in this cluster than in the luminous parts of galaxies that shine, that are stars, that are planets, that we know about, all the stuff that we know about. And all of these different measurements are leading to the same result. So whereas in the 1930s and up until the 1970s, you could say, well, maybe the results aren't correct. Now it's unambiguous. There's no question that there is something else there that's causing these motions, that this dark matter is interacting via gravity. It's obeying Newton's law of gravity, but we can't see it. So what could this dark matter be? And there are lots of ideas, in particular in the 1980s and 1990s, astronomers looked very hard to see what the dark matter could be made out of. And there are a lot of ideas. If you put down a list of possibilities, you might say, okay, there are rocks, maybe there are planets, lots of planets out there. Maybe there are old stars that have burned out and we don't see the remnants of the earlier stars. Maybe there is cold gas in addition to this hot gas I spoke about. Maybe there's more hot gas than we know about. Maybe they're very compact objects, massive ones that we just haven't discovered yet, haven't seen them, they don't emit light. Maybe they're black holes. We know of the existence now of black holes. Maybe they're dust, particles of dust. Or maybe they're an as yet undiscovered new particle that we don't know about. And this is just an example that shows that these are the motions of stars in galaxies. That was another piece of evidence. The stars are moving faster than what you expect based on what you see in the luminous parts of galaxies alone. Astronomers ruled out every one of the possibilities in white. It's not there. They literally spent 2 decades looking for it. It's not there. And we would see evidence of those things if that was what explained the dark matter. And the only possibility that has remained is that there may be a particle. Astronomers now think, and physicists think, that it was a particle formed soon after the Big Bang that interacts by gravity but does not emit light. We cannot see it, but its effects are there in the motions of stars and galaxies and gas that we do see. And so there's a lot of effort in underground laboratories, physics laboratories around the world. The Large Hadron Collider, which is in between France and Switzerland, the particle accelerator, looking for the effects of dark matter. And it's something that physicists and astronomers really hope will happen in the next decade. They're searching very hard, but we still, as yet, do not know the nature of dark matter, although there are some good ideas for what it might be, and that's what astronomers and physicists are now looking for. So just to summarize, this is what I'm an observer, I use telescopes. This is what we see when we look at the universe. It's full of galaxies, full of stars. It's lumpy. There are lots of galaxies in different regions of the sky. They have different densities over different parts of the sky, but it's filled with stuff. So here's a theorist's view of the universe. Anyone believe this is an actual image of dark matter? It's not. Yeah, but we have no detection yet of what the dark matter is. We have ideas for what it is, but we, at this point, are waiting to determine what the nature of dark matter is. And there appears to be about 6 times as much dark matter as there is luminous matter in the universe, the stuff that we're made out of. And this is showing, these are computer simulations where in a computer you put in particles that simulate the matter within galaxies. This is the dark matter shown here. And you let the dark matter interact by gravity and assemble over the history of the universe. And you can see that over time you build up the structures that we see in clusters of galaxies and long filaments of galaxies that have been discovered in the last few decades. So starting from what are just the tiny fluctuations in density for which we see evidence from the cosmic microwave background, the remnant radiation from the Big Bang, just due to the noise due to quantum fluctuations in the early universe. That's the only assumption in these models, these computer simulations. You end up with things that in the end look very similar. And here on the left is showing where the luminous matter is. It tends to cluster in the same places as the dark matter because it is interacting by gravity. So you end up with a universe, this is what we see in galaxies, but this is what's actually out there, the dark matter, which is most of the matter determining where the galaxies are and how they're interacting. So that was a completely unexpected result. And as I mentioned, this is a very active area of investigation. People are using detectors that are very sensitive, shielded. They're underground in mines, for example, around the world, so you can block out the radiation coming from the atmosphere, from cosmic rays, to look for the tiny signals of these dark matter particles that might be inducing sound waves in the nuclei of atoms. And the limits have gotten much more severe. Physicists have been looking for the evidence of dark matter. So far, haven't found any. But the best models indicate that if it's there and it's what people think right now, we should be seeing that in the next decade. So that could be a very exciting discovery, and we're very much hoping that it will be found within the next decade. So the universe is accelerating. We know that by observing these very bright stars, supernovae. These are stars that are located in a binary system, two objects. And you can see one of the stars here is losing matter. It's falling onto this companion here, which is a very dense object. It's called a white dwarf. And when enough matter has gone onto the white dwarf, the star explodes into what we refer to as a supernova explosion. And these explosions are so bright that for about a very short amount of time, they actually can rival the brightness of an entire galaxy, which is why we can see them so far away. And so in the 1990s, two groups decided to go look for what they were imagining would be the deceleration, the slowing down of the expansion that had been discovered by Hubble. You expect the expansion to slow down because of gravity, right? If I throw something up, I'm not going to throw this, don't worry, whoever owns it. I throw it up in the air, it's going to fall down due to gravity. If I give it enough of a kick, like a rocket, it will escape the Earth's gravity and keep going. But because of gravity, we know things will actually fall back down to the Earth. What got discovered, instead of deceleration, instead of the universe slowing down because of the presence of matter in the universe, which is what astronomers had expected, it's as if I threw this up, and not only did it have enough of a kick to escape the Earth's gravity, but it went even faster, escaping, accelerating, speeding up in its expansion. And that's what these two groups discovered at the end of the 1990s, for which the Nobel Prize in Physics was awarded a few years ago. The universe is speeding up in its expansion. And how does that happen? What could cause that? We don't know. And at the present time, there are lots of ideas out there, but I'd say no good ones. Okay, so the universe is accelerating, speeding up with time. And it's something that has been referred to as the biggest mystery in science. We don't know what is causing the universe to speed up. Now, one of the possibilities is that something called the cosmological constant that was actually predicted by Einstein. It was a term that he put into his equations for general relativity. And the reason that he put this term into his equation for gravity was that there was no evidence for a universe that was in motion. That is, if you look at stars in the sky, remember Edwin Hubble didn't discover the expansion of the universe until 1929. Einstein was working on his theory of gravity in 1915. No evidence for any expansion. And what he knew was either the universe would have to contract because of gravity or it would have to expand, but it couldn't just be static, unmoving. It would have to do one or the other. So he put something he called the cosmological constant, which is a mathematical term, no physical understanding of what it was, to force the universe not to expand or contract. And then when Einstein in 1929 discovered that the universe was expanding, Einstein was reputed to have said that this was his biggest blunder ever. It turns out, however, that this cosmological constant may be what is responsible for the acceleration of the universe. It's perfectly consistent with that idea. It's a repulsive form of gravity. The only difficulty is that the amount that would be predicted is about 120 orders of magnitude, by which I mean 1 followed by 120 zeros. Wrong. What we see in dark energy is tiny. The only reason that it has the effect that it does, and that it comprises 70% of the overall mass and energy in the universe, is that the universe, the volume is so big. So there remains no good theory at the present time for what is causing the acceleration, but it could be consistent with Einstein's cosmological constant. It appears to be consistent in its properties, but the amount is simply wrong, and that no one at the present time understands. So if there are any young people in the audience who think that everything's already been done, there's a problem waiting for you to solve, which badly needs solving. We don't understand that. So the outstanding mysteries are that 1/3 of the universe appears to be made of matter, 2/3 of it's made of dark energy, and we don't know what the nature of 95% of what is in the universe. is made of. About 1% appears to be in stars. That includes stars, planets, us. And the rest, about 4% of it is ordinary dark matter that we don't see, and 25% this dark matter that is probably a particle left over from the Big Bang that I described. Okay, so now I'm going to turn to Las Campanas again, go back to astronomical observatories and the now development of new telescopes for this 21st century. So here's the Magellan Telescope. This is one of the 6.5 meters that is already at Las Campanas, and these are just some very pretty pictures taken on the mountain. Believe it or not, there actually are clouds, unfortunately. Sometimes you can't observe when it's cloudy. But most of the year, about 300 nights a year, are clear at Las Campanas. It's one of the best sites in the world. And it's the site of our future Giant Magellan Telescope. So the Giant Magellan Telescope is a 25-meter telescope. It's made up of 7 mirrors, 6 of them shown here in a circle, sort of a flower petal arrangement. One is in the center. It's housed in a building that is 60 meters high. That's like 22 floors in the building. Only, as I'll show you in a minute, the whole building has to rotate so that we can point the telescope out at any region, any direction in the sky. So it's a very ambitious project. There's nothing like a telescope this big in existence at the present time. And if it had been easy, we would have done it already. So the telescope itself stands 43 meters high. You can see for reference here some little figures. It's very large. Looks lightweight, but these are very rigid pieces of steel that provide the structure to the mount that holds the mirrors and keeps them stable as the whole telescope itself has to move during the night. So this is a view of Las Campanas. This is the peak where the Giant Magellan Telescope will go. That's the building that will house the telescope. And this is a place where the mirrors will actually be coated with a surface of aluminum. So just coming around to the side of the mountain, we've actually leveled the top of the mountain. That was done in 2012 to allow us to do that. So here's the support building, and here's the building itself. Opens up to the night sky, and you can see these open pieces here where ambient air from the outside can blow through the enclosure during the night, and we're trying to keep the temperature on the inside of the enclosure as similar to the outside as we can. If there's differences in temperature, you can see the mirrors here, but if there are differences of temperature around the surface of the mirror, that causes turbulence, and it ruins and you can see now how the front part of the building can move up, and the telescope can be locked into safety here. And this shows just another view of the telescope where you can see the mirrors in more detail. And the person who put this together actually is basing it on the engineering designs for the telescope. But you can see these reflections off the mirrors. Of course, galaxies aren't that bright. So our work is a little more difficult in actually making these measurements. But here is showing the mirrors. There'll be cells that the mirrors go into. We are a little more careful than shown in the video, and that's how they'll be assembled. The technology for making these mirrors is actually very interesting in its own right. It's developed by an astronomer at the University of Arizona, so you can see all 7 of the mirrors here. And the primary mirrors, these big ones, each of them is 8.4 meters in diameter, so 7 of those. And there'll be 7 smaller, what we call secondary mirrors, up near the top of the telescope. And those mirrors are only 1 meter in diameter. The big ones are 8.4. And those can move much faster because they're much lighter. And these ones will actually be used to correct the distortions caused by the turbulence in the Earth's atmosphere. So those corrections will be made on a timescale of thousandths of a second. And the bigger mirrors are corrected every 30 seconds or so. And there'll be mechanical actuators on the back of the mirrors, almost 5,000 of them, that will push and pull. And so even though these mirrors are heavy, made of solid glass, as the telescope is moving through the sky, the mirror is distorted in shape. And if we're going to get this resolution, which is now going to be 10 times the resolution of the Hubble Space Telescope, which for astronomers is the benchmark for what we've been able to do until now, that allows us to make those corrections with this very large telescope, 10 times that of the Hubble Space Telescope. Showing you. So the GMT is going to have 20 million times the sensitivity of your eye, which is quite a staggering number. And just to give you some sense, if I was holding a coin and I was looking at it, I could read the writing on that coin. If it was right in front of me, I could see a face on that coin if there's a face on the coin. But probably even in the front row, you could not read the face of that coin. But if we were sitting here with the GMT, which actually is, maybe it's the size of this auditorium, actually looks fairly similar if you go behind me, and we turn that telescope and someone was holding a coin in Córdoba, you could actually resolve what is on the face of that coin. That's how powerful this telescope will be. And if I were standing on the moon and holding a candle and you were here looking with the GMT is sensitive enough to actually see a candle on the moon. So you can see why astronomers are very excited about this new capability. It's something that we have not had this extraordinary technical capability before. What will allow us to do? One of the things is to measure the first starlight in the universe, the first galaxies that formed, that period that I told you at the beginning we call the dark ages, where we just don't have enough sensitivity and certainly not the resolution, the fine detail to be able to see what's forming. So for the first time, we will actually look back and witness directly what happened when the first stars formed. We know that there were small fluctuations in the microwave background, the temperature and the density. We know we are in a galaxy today. We see other galaxies, but we don't know how it happened. And for the first time, we'll be able to see that actually happening when it started early in the universe. The whole question of exoplanets and that subject has just blown open. There are many different kinds of worlds out there. There are very hot, big planets, giant planets like Jupiter and Saturn, only close into the stars, unlike Jupiter and Saturn in our own solar system. There are ice giant planets. There are planets that have more water than we see on Earth, may be entirely water. There are super-Earths, planets with a few times the mass of the Earth. It was even speculated at one point that there might be diamond worlds, although it's unclear whether that result will hold the test of time. But what has become really clear is that it is a tendency, a natural tendency for us to think that planets will be, or anything will be like what we know about, including matter in the universe. We assume it's like us. But there are things out there that we're now discovering that are nothing like what our own solar system is like. And I think the next decade in these new telescopes are going to reveal even more surprises. It won't anymore just be the world of science fiction. There actually now have been a planet orbiting two stars, which those of you who know Star Wars, that's no longer simply science fiction. And what is about to happen is the capability to discover planets like the Earth. There are candidates now that appear to be similar in size to the Earth, but we don't yet have the sensitivity to actually measure the velocities, the orbits of those planets, from which, using Newton's laws, we can determine the masses for those planets. And those will be discoveries that the giant Magellan Telescope will make. There's a possibility that we could actually take spectra, disperse the light that we're seeing from the atmosphere of those planets, like a rainbow, what happens when we put light through a prism, and look for the signatures of things like carbon dioxide, water, ozone, that are signatures of life on Earth. And so it may be possible to actually distinguish between pure chemistry. You can get carbon dioxide from chemical processes, but we know that the evolution of the atmosphere on the Earth, the increase in oxygen, came about from the development of life, the evolution of life. And so I think one of the really exciting possibilities in the next decade or so is that when we get these new facilities, we are actually going to be asking questions about whether or not life exists elsewhere in the universe, which I think would be an extraordinary and historical discovery. So just briefly, let me tell you, the partnership to build the GMT is an international one. There are a number of institutions across the United States and in Brazil now, our most recent partner. Chile is involved, Australia, and also South Korea. And we have just, in fact, in the last couple of weeks, raised the funding to allow us to begin to go ahead with construction. So that's a huge milestone for us. And we're going to be beginning construction in 2015. So these are the partners that are involved in the telescope, including the University of Chicago, where I now am, and Carnegie Institution, where I was. So the mirrors are made at the football stadium at University of Arizona. Just to show you very quickly, the technology that's used is actually to melt the glass in an oven that is spinning 5 times a minute. You put in giant chunks of glass, let the glass melt, and then because it's spinning, just as if you had a pail of water and you spin the pail of water, the glass comes up to the edge because of the force pushing it out due to the spinning motion. And that gives you the original parabolic shape that you need for your mirror. It's just a flat piece of glass, light coming in, which is bounced straight up. You need to bend it so we can focus it and look at the images that are coming to us from these distant objects. And this is showing the assembly of one of our mirrors. These mirrors now have been polished. We've finished the first one, and the surface of the mirror has been polished to an accuracy of 20 billionths of a meter. So that is the roughness of the surface is less than 20 billionths of a meter. Never been done before, certainly not on this kind of scale. It's extraordinary. But that's what allows you to have a resolution to see fine detail 10 times that of the Hubble Space Telescope. So it's extraordinarily difficult. Took 8 years to complete the first mirror, but it's been done. And that will be 10 times better than Hubble in resolution. And I mentioned earlier we're going to be correcting for the blurring of the Earth's atmosphere to actually take the distortions, as shown in Van Gogh's Starry Night, the waves that are coming to us from the light distant parts of the universe, and actually correct them and take out these distortions. So just to give you some sense of what that looks like, this is an image that is taken with a telescope on the ground right now, one of the 8-meter telescopes, and it is a region of in a nearby galaxy where there are stars forming, a cluster of stars. So if you look at these big images here, these blobs, just get a sense of what that looks like. This is what the same region will look like. You see these blobs again, these stars, when you go to what will be the successor of the Hubble Space Telescope, the James Webb Space Telescope that we launched in 2018. And you can see that there are more blobs. So in addition to the big blobs, some smaller stars are now, we can see, coming into finer detail. And this is what it will look like with the giant Magellan Telescope. So you can see this extraordinary, look at these tiny, faint stars that suddenly come out. And just to compare again, so that's what it looks like with our current best telescopes from the ground. That's what it will look like with the giant Magellan Telescope. So the numbers of things that we can study, so these early galaxies in the universe and star-forming regions in nearby galaxies, these questions of dark energy, the nature of dark matter, and planets around other stars, every subject in astronomy essentially is going to be revolutionized by this kind of new technology, which is, again, why we're so excited about it. So 2012, we blasted off the top of the mountain and to make room for the telescope, and that's the site before the blasting. So you notice the rubble and the road here that have been cut. And now if we just take a look at what it looks like after, so watch here. That's now the site where the telescopes will go. So there'll be 250 people working in the construction of the telescope, starting at the end of this year is when we plan to start. So that's us today. This is the sequence of the mirrors, and by 2021, we will have 4 of the mirrors in the telescope, 2 scientific instruments, and so the blasting in 2012. We're starting construction this year, and first light will happen in 2021. So I hope I've shown you that the last century has been one of unexpected discoveries. We've completely changed the nature of our understanding of the universe that we live in, the discovery of the expansion of the universe, the existence of dark matter and dark energy, and the new discovery of planets outside our solar system. And I hope I've managed to convey some of the excitement for the new facilities that we're building in the next decade that I think are likely to reveal even more surprises. So let me stop there. Thank you.